We're going to start with our background for radioactivity, and what you see here, it's a bit busy, 3 different materials, green, pink, and yellowy orange. They have different rates of decay. We all start with 8 particles and then the number decays. Now I've drawn straight lines here through the points. I have few points. You know that I'm cheating. You can't have fractional points, but in reality this would be millions of particles, and all the dots then could be written as straight lines or curved lines. We can join the dots in effect. So let's start with pink. We all start with 8. And it decays in this fashion. And the formula that describes the number of particles left is this one. So let's go through this for each of the materials and draw some conclusions. At t equals 0, 2 to the 0 for all of these materials is always 1. 8 times 1, 8 times 1, 8 times 1. At t equals 0, we're sitting right there. Let's go through one time step for pink. So at time 0, we have 8. At 1 second, 2 to the minus, well, it's just going to be 1, 2 to the minus 1. What's that? This is the key point right here. Notice that I've written 2 to the minus 1 is a half with this glowing globe around it. So at 1, this is 2 to the minus 1. 8 times a half is 4. That is the half-life for pink. And let's put t equals 2. 2 to the minus 2 is a quarter. A quarter of 8 is 2. And 3. 2 to the minus 3 is an eighth. An eighth of an eighth is 1. So that's the pink curve. Something that decays slower is the green curve. So we start again at t equals 0, it's 8. This is the model. Notice this number is smaller. It should be, I could have put a 1 here. This is smaller. So at t equals 2, we get 2 divided by 2, which is 1. 2 to the minus 1 is a half. Half of 8 is 4. So at 2 seconds, we have 4 particles left. And at 4 seconds, t is 8 times 2 to the minus 1/2 of 4. 1/2 of 4 is 2. 2 to the minus 2 is a quarter. We have 2 particles left. At 6 seconds, 6 over 2 is 3. 2 to the minus 3 is 1/8. We have 1 particle left. The half-life is 2 seconds. Now, the third one is this yellow one here, and it goes fast, and I've made it as minus 2t. So at t equals half a second, we got 2 times a half, which is 1, and 8 times a half is 4, and then it goes down from there very, very quickly. Now, the half-life for this fast decaying material is half a second. Now I want you to see a pattern here. This should be 1, so that corresponds to that. No big deal there. But look, the half-life here appears in reciprocal form there. So the half-life is 2, but this constant, which is called the rate constant, is a half. The half-life is a half. 1 over a half is 2. The rate constant is 2. So the rate constant and the half-life are reciprocally related. And so in this case, we can say that t half is equal to 1 over the rate constant. Now, this is the model when we've got simple doubling or reducing by 2 every time. Notice that t would be in seconds, so the rate constant has to be 1 over seconds, because you'd have 1 over seconds gives me seconds. It's per second. For radioactive materials, it'll be per year or maybe per thousands of years, depending on how quickly or how slowly the material decays. Now we're going to apply this to the real world where we're going to see that we don't use 2 as our base for decay. But the final result is going to be very similar to what we have, so that the half-life is 1 over the decay rate.